The star is right there. That is the maddening thing. You can point to it, or rather, point to the general region of sky where it hides, too faint to see without a telescope, lurking in the southern constellation of Centaurus like a dying ember, Proxima Centauri, the closest star to our Sun, and around it a planet. A rocky, Earth-mass world sitting right in the middle of the habitable zone, close enough that liquid water could pool on its surface. Close enough, in cosmic terms, to feel like a gift. And yet how long would it actually take to get there? What would the journey do to the people aboard? What would they find when they arrived? And could the ship even survive long enough to deliver them? These questions have been sitting in the minds of scientists, engineers and dreamers for decades, growing more urgent with every new discovery. But the answers, the real answers, stripped of science fiction and wishful thinking, are stranger and more troubling than almost anyone expects. This is the story of that journey, not the version where humanity solves everything with a hand wave. The version where physics shows up, uninvited, and starts breaking things, where the gap between 4 light-years and 0 light-years turns out to contain enough obstacles to humble every civilization that has ever looked up at the stars and said, "We should go there." There is a peculiar human habit of underestimating distances by failing to feel them. We are told that Proxima Centauri is 4.24 light-years away, and we nod, we accept the number, we place it somewhere in the category of very far, and we move on. But the number does not land. It cannot land, because the human nervous system was not built to feel light years. Our emotional repertoire of distance tops out somewhere around the Pacific Ocean. Everything beyond that is just abstraction, and abstraction is the enemy of awe. So let us try to feel it. A light year is the distance light travels in a single year, moving at 299,792 kilometers per second, a speed so extravagant that light could circle the entire Earth 7.5 times in 1 second. In 1 year, light covers approximately 9.461 trillion kilometers. Proxima Centauri sits 4.24 of those years away. That is roughly 40,140,000,000 kilometers, 40 trillion kilometers, from where you are sitting right now. If you printed that number in standard digits across a page of text, it would take you a moment to count all the zeros, and then a much longer moment to convince yourself it was real. But still the number refuses to land. Numbers never land. Comparisons are better. Voyager 1 is humanity's fastest and most distant spacecraft. Launched in September 1977, it has been hurtling outward through the solar system and beyond for nearly 5 decades, and as of 2026 it sits approximately 25.8 billion kilometers from Earth, a distance so staggering that radio signals, travelling at the speed of light, take more than 22 hours to make the one-way trip. 22 hours for a signal moving at the speed of light. And yet, against the backdrop of the journey to Proxima Centauri, Voyager 1 has barely left the driveway. It is travelling at roughly 17 kilometers per second, fast enough to cross the continental United States in about 4 minutes, slow enough that it would take approximately 73 zeros and years to reach Proxima Centauri if it were aimed in that direction, which it is not, 73,000 years, longer than the entirety of recorded human history, longer than the time since Homo sapiens first painted animals on the walls of caves in what is now Indonesia. The entire sweep of human civilization, the pyramids, the Roman Empire, the Renaissance, the Industrial Revolution, the Space Age, all of it fits comfortably inside about 10,000 years. Voyager 1 at its current speed would need 7 complete replays of human civilization, end to end, before it nudged within reaching distance of our nearest stellar neighbour. This is where the story of interstellar travel always begins, and it is not a comfortable place to begin. And yet, here is the part I find genuinely arresting, the part that I keep returning to. We know there is something worth reaching, because on the 24th of August 2016, a team led by astronomer Guillaume Anglada Escudé published a paper in the journal Nature that changed the terms of the conversation permanently. After years of careful observations, using the high-accuracy radial velocity planet searcher instrument at the European Southern Observatory in Chile, they detected a subtle, rhythmic wobble in the motion of Proxima Centauri, the telltale gravitational signature of an orbiting planet. The planet, designated Proxima Centauri b, has a minimum mass of 1.055 times that of Earth. It completes one orbit every 11.2 days, and, the part that made headlines around the world, it orbits within the habitable zone of its star, the range of distances where temperatures could allow liquid water to exist on the surface. Think about what that means for a moment. The closest star to our Sun hosts a rocky Earth-mass planet in its habitable zone. The nearest shore is not empty sand. There may be something there. There may be something extraordinary there. Since that original discovery, the Proxima system has only grown more populated with possibility. In January 2020, a team published evidence for a second planet, Proxima Centauri c, a super-Earth with roughly 6 times the mass of our world, orbiting much farther out with a period of 5.3 years. Then in 2022, the European Southern Observatory announced evidence for a third candidate planet, Proxima Centauri d, a lightweight world at just 1/4 of Earth's mass, orbiting extremely close to the star with a period of just 5 days, making it the least massive exoplanet ever detected using the radial velocity method at that time. 3 planets, in the nearest star system, 4 light-years away. The Proxima system is not just our closest stellar neighbour, it may be our closest planetary neighbourhood. But let us be precise about what Proxima Centauri actually is, because precision matters here, and the reality of this star is both more modest and more violent than most people appreciate. Proxima Centauri is a red dwarf, an M-type star of spectral class M55V, which tells you several things at once. It is small, roughly 12.5% of the Sun's mass, so lightweight that it barely cleared the threshold required to sustain hydrogen fusion in its core. It is dim, it shines at 0.0017 times the luminosity of the Sun, which is why you cannot see it with the naked eye despite being our nearest stellar companion. It is cool. Its surface temperature runs around 3042 Kelvin, compared to the Sun's 5778 Kelvin, and it is old, at approximately 85 billion years of age. It is slightly older than our Sun, though red dwarfs are so miserly with their fuel that they can burn for hundreds of billions of years, outlasting Sun-like stars by orders of magnitude. This is also why Proxima Centauri is the nearest star to the Sun. Not because it has a particularly special position in the galaxy, but because red dwarfs are by far the most common type of star in the Milky Way. They account for roughly 70% of all stars, and so statistically, it makes sense that our nearest neighbour would be one of them. If you look at the 60 nearest stars to our Sun, approximately 50 of them are red dwarfs. We are surrounded by dim, long-lived, modest little embers, and Proxima is the closest of all. There is also the matter of Proxima's relationship to the Alpha Centauri system. Alpha Centauri, the third brightest star in Earth's night sky as seen from the southern hemisphere, is in fact a binary system. 2 stars, Alpha Centauri A and Alpha Centauri B, gravitationally bound and orbiting their common centre of mass with a period of roughly 79.9 years. Both are broadly Sun-like. A is slightly larger and brighter than our Sun. B is slightly smaller and dimmer. Together, they form one of the most studied binary systems in astronomy, and Proxima Centauri, at a distance of roughly 0.21 light-years from the AB pair, is gravitationally bound to them as well, though loosely, taking approximately 550,000 years to complete one enormous orbit around its 2 companions. This makes Proxima Centauri technically a member of a triple star system, which is the whole Alpha Centauri complex. 3 stars, 4 known planets, at minimum, and a combined distance from Earth of between 4.4 and 4.37 light-years, depending on which member of the family you are measuring. This is the destination. The nearest shore of the cosmic ocean. And we want to go there. We have wanted to go there since the moment we understood what stars actually were. The question is not whether we want to go. It is whether we have any idea what we would be getting ourselves into. And the answer, once you begin pulling at the threads of physics, biology, engineering, and probability, is that we do not. Not fully. Not yet. The journey to Proxima Centauri is not simply a long journey. It is an encounter with every limit that nature has placed on the ambitions of any species that evolves on a warm, wet planet and then has the audacity to look upward and imagine leaving. There are three great unsolved puzzles at the heart of this endeavour, and I want to name them now because they will haunt every chapter that follows. The first is the propulsion problem. How do you get a spacecraft or a crew to Proxima Centauri in anything less than geological time? The second is the survival problem. What does the journey do to the human body, the human mind, and the physical structure of the ship itself? And the third is the arrival problem. Even if you make it there, even if you pull into the Proxima system somehow intact and alive, what happens when you look around and take stock of what you have actually found? These three problems nest inside each other like Russian dolls. Solve the first and the second becomes more acute. Solve the second and the third becomes more urgent. And the third, the arrival problem, opens into a question so deep and so strange that it does not resolve so much as expand. But we begin where every great journey begins, with the question of how on Earth, or rather how off Earth, you could possibly get there. Let us be honest about the state of play. The fastest human-made objects in history are the Helios solar probes launched in the 1970s, which reached speeds of approximately 2 kilometers per second as they slung close around the Sun. At that speed, which represents the outer edge of what chemical and gravitational assist propulsion has ever achieved, a journey to Proxima Centauri would take approximately 18,150 years. This is an improvement on Voyager 1's 73,000-year estimate, but it is not an improvement that brings the destination within anything resembling a human timescale. 18,000 years ago, Homo sapiens had not yet developed agriculture. The first cities would not emerge for another 9,000 years. We are asking whether we could send a crewed spacecraft on a journey longer than the entire arc of human civilization, and whether the people aboard could survive it, and whether anyone on Earth would still care when it arrived. They would not. They could not. The civilization that launched the mission would be unrecognizable or extinct long before the ship entered the Proxima system. So chemical propulsion is off the table for any mission with human ambitions attached. It simply cannot bridge this gap. The numbers are too brutal, and this is where the conversation about propulsion becomes genuinely extraordinary, because the serious ideas that have emerged from serious scientists and engineers over the past century are ideas that sound, at first encounter, like the most extravagant science fiction ever committed to paper. Nuclear pulse propulsion is the oldest of the credible candidates, and it has a lineage that might surprise you. Project Orion was a classified and then semi-public research program run in the late 1950s and through the 1960s, backed by the United States Air Force and later NASA, and it proposed the following mechanism for travel. You detonate nuclear bombs behind a large pusher plate at the rear of the spacecraft, and the expanding plasma from each detonation pushes the plate and the ship forward. Each explosion provides an impulse. Enough explosions in rapid succession provide sustained acceleration. The mathematics work out to be remarkably favourable. Orion studies suggested that a fission pulse spacecraft could reach velocities of roughly 3% of the speed of light, while a more advanced thermonuclear pulse design might achieve 8 to 10% of light speed. At 10% the speed of light, the journey to Proxima Centauri would take approximately 42 years. Still a long time, still a human lifetime, or close to it, but no longer geological time, no longer absurd. The reason Project Orion was never built comes down not to physics, but to politics. A partial test ban treaty of 1963 prohibited nuclear weapons detonations in the atmosphere, in space and underwater, and Orion's propulsion system would have violated all three with every single firing. The treaty was the right call for Earth. For interstellar travel, it was a door that quietly closed. The next serious attempt to design an interstellar probe was Project Daedalus, a study conducted between 1973 and 1978 by the British Interplanetary Society. Daedalus was a two-stage fusion pulse spacecraft, not fission but nuclear fusion, designed to travel to Barnard's star approximately 5.96 light-years from Earth. The concept used pellets of deuterium and helium-3, compressed and ignited by electron beams, detonating at a rate of 250 pellets per second in a reaction chamber. The mathematics projected a final cruise velocity of approximately 36,000 kilometers per second, 12% of the speed of light. Stage 1 would burn for 2.5 years, Stage 2 for 1.76 years. Total mass at launch, roughly 54,000 tons, of which approximately 50,000 tons was fuel. The payload, the scientific instruments, the probe structure itself, was a vanishingly small fraction of the total. This is the nature of rocketry. Fuel dominates everything, and the more ambitious your destination, the more mercilessly it dominates. Daedalus had one crippling flaw that the study's authors openly acknowledged. There is almost no helium-3 on Earth. The fusion fuel the design required exists in meaningful quantities on the Moon, embedded in the regolith over billions of years of solar wind bombardment, and in vastly larger quantities in the atmospheres of the gas giants, particularly Uranus and Neptune. To fuel a Daedalus mission, you would first need to develop industrial-scale helium-3 mining operations in the outer solar system. Daedalus was not a plan for the near future. It was a plan for a civilization considerably more capable and far-flung than our own. The successor project, Project Icarus, was launched by the British Interplanetary Society in 2009 as a comprehensive redesign of the Daedalus concept, with one crucial modification. Daedalus was designed purely as a flyby mission. It would pass through the Barnard's star system at 12% light speed, spending only a few precious hours in the vicinity of its target, before careening on through interstellar space forever. Icarus required the probe to be capable of decelerating at the destination, to actually enter orbit around the target star and conduct sustained observations. This sounds reasonable. It is, in engineering terms, nearly catastrophic. Decelerating a spacecraft that has been accelerated to a significant fraction of the speed of light requires as much energy as accelerating it in the first place. You need, in effect, to do the whole propulsion job twice. The fuel requirements, already staggering, roughly double. The launch mass, already enormous, expands toward numbers that strain comprehension. This is what physicists call the deceleration problem, and it is one of the most persistent and underappreciated obstacles in interstellar mission design. Getting there is hard. Stopping when you get there is, in many respects, harder. There are proposed solutions: a magnetic sail, a vast loop of superconducting wire, creating an electromagnetic field that interacts with the stellar wind of the destination star, could theoretically provide braking force without consuming propellant. The star's own wind of charged particles would push back against the sail, slowing the spacecraft. This concept, first proposed by Dana Andrews and Robert Zubrin in the early 1990s, is elegant in principle and deeply uncertain in engineering. The superconducting loop would need to be enormous, hundreds of kilometers across, to provide meaningful braking at interstellar approach velocities. The manufacturing, deployment, and reliability of such a structure in deep space, after decades of travel, is a challenge that has not been solved. Another proposed solution is the laser sail, and this is where the conversation arrives at what is, to my mind, the most genuinely audacious interstellar project in the history of human civilization. Breakthrough Starshot was announced in April 2016 by the Breakthrough Initiatives program, co-founded by physicist Stephen Hawking and Russian billionaire Yuri Milner. The concept is startlingly simple in its broad strokes and terrifyingly complex in its engineering details. You build a ground-based laser array, initially conceived at a power level of 1 gigawatt, later discussed at up to 100 gigawatts, and you use it to illuminate a sail made of an ultra-thin, highly reflective material. The sail is attached to a miniaturized probe, a nanocraft weighing no more than a gram carrying cameras, sensors, communication systems, and a power supply. The laser fires, the light pressure accelerates the sail, and within minutes the nanocraft reaches approximately 20% of the speed of light, 60,000 kilometers per second. At that velocity, the journey to Proxima Centauri would take roughly 20 years, within a human lifetime. The same individual who watched the launch could, in principle, still be alive and paying attention when the first signals came back from the Proxima system. The numbers here are worth holding. A 100 gigawatt laser is approximately 100 times more powerful than the total electricity generating capacity of a large nuclear power station. Building it is not beyond the known laws of physics, but it is far beyond the current capacity of any engineering program on Earth. The sail material needs to reflect more than 99.999% of the laser light that strikes it without melting, warping, or delaminating. And it needs to do this while being accelerated at tens of thousands of times the force of gravity within a few minutes of launch. The nanocraft itself needs to survive 2 decades of travel through the interstellar medium, a thin soup of dust particles, hydrogen atoms, and high-energy cosmic rays, and then, upon arrival at Proxima Centauri, conduct scientific observations and transmit them back to Earth at a transmission rate that allows the data to be recovered. Communication time at that distance, 4.24 years at the speed of light, one way. Send a message from the probe. Wait 4.24 years for it to arrive. And there is the deceleration problem again, the cruelest problem of all. Breakthrough Starshot's nanocraft would not stop at Proxima Centauri. It could not. There is no mechanism aboard to slow it down. It would pass through the system at 20% of light speed, spending perhaps a few hours in range of meaningful observations before shooting out the other side and vanishing into interstellar space permanently. It is a fly-past mission, better than nothing, far short of everything, a proof of concept with a built-in expiration date on its scientific return. A crewed mission is a different universe of challenge entirely. Human beings cannot survive a fly past. They cannot observe a planet from 60 raw kilometers per second and learn anything meaningful. They need to arrive, decelerate, enter orbit, deploy instruments, analyze data, make decisions, adapt to surprises. They need to stop, and stopping a crewed spacecraft that has been accelerated to any meaningful fraction of light speed requires fuel. Enormous, almost incomprehensible amounts of fuel, unless you can find a way to harvest that fuel from the interstellar medium itself. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, imagined exactly this: a spacecraft with a vast electromagnetic scoop, hundreds of kilometers wide, that would collect hydrogen from the interstellar medium and funnel it into a fusion reactor, burning the hydrogen as fuel. The ship would accelerate continuously. The faster it went, the more hydrogen it scooped, theoretically achieving speeds approaching the speed of light and eliminating the fuel mass problem entirely. It is an extraordinarily beautiful idea. The physical problems with it are equally extraordinary. The interstellar medium turns out to be far less dense in hydrogen than Bussard had hoped, roughly 1 atom per cubic centimetre on average, and the drag created by the electromagnetic scoop would likely exceed the thrust generated by any plausible fusion reaction with the collected fuel. The ramjet, as originally proposed, does not work. Modified versions, using the scooped hydrogen for braking rather than propulsion, remain theoretically interesting, but practically, we do not know how to build an electromagnetic scoop hundreds of kilometers wide that could function for decades without failure. Antimatter propulsion offers the most thermodynamically efficient pathway of all. A matter-antimatter annihilation reaction converts 100% of the combined mass of reactants into energy, compared to roughly 0.7% for nuclear fusion and less than 0.1% for nuclear fission. A kilogram of antimatter annihilated with a kilogram of ordinary matter releases approximately 1.8 times 1017 joules of energy, the equivalent of roughly 43 megatons of TNT, enough, in principle, to accelerate a crewed spacecraft to a substantial fraction of light speed. The problem is the same as it has always been. Producing antimatter is preposterously expensive, slow, and energy-intensive. The combined production capacity of all the particle accelerators on Earth generates on the order of a few billionths of a gram of antimatter per year. To fuel even a modest interstellar mission would require quantities of antimatter that current technology could not produce in the lifetime of the universe. We are not even in the wrong order of magnitude. We are in the wrong conceptual universe. And yet, here is where I feel the particular quality of wonder that this topic generates, and I want to be honest about it. None of these problems are violations of known physics. Every single one of them is an engineering challenge, a resource challenge, a civilizational capacity challenge. They are not impossibilities, they are difficulties. The universe has not actually told us we cannot go to Proxima Centauri. It has simply told us that getting there will require us to become something more than we currently are. The question is, what would it cost us to become that? And what would it cost the people who made the journey itself? The propulsion problem, enormous as it is, may not be the hardest part of the story, because once you have built the fastest spacecraft in human history and pointed it at Proxima Centauri, the journey it has to make will begin breaking things that no engineer ever put on a blueprint. Picture for a moment the interstellar medium. We use the word void for interstellar space, and the word is mostly accurate, but mostly conceals a great deal. The space between stars is not a perfect vacuum. It is a thin, cold, turbulent sea of material. Neutral hydrogen atoms, ionized plasma, molecular clouds, dust grains, magnetic field lines threading through everything like invisible wire, and a continuous rain of high-energy particles streaming in from every direction at nearly the speed of light. This last category, galactic cosmic rays, is the aspect of the interstellar medium that should concern any mission designer most deeply, and it does not receive the attention it deserves in popular discussions of interstellar travel. Galactic cosmic rays are not exotic phenomena. They are a permanent feature of the universe, generated by the shockwaves of supernova explosions, the jets of active galactic nuclei, and various other high-energy astrophysical processes. They consist primarily of protons and atomic nuclei, hydrogen, helium, carbon, iron, stripped of their electrons and accelerated to velocities approaching the speed of light. They carry enormous amounts of energy. A single iron nucleus cosmic ray can carry more kinetic energy than a baseball thrown by a major league pitcher, compressed into a subatomic particle, and they arrive continuously from all directions at a rate that is easily manageable for brief space missions, but becomes increasingly hazardous over years, decades, and centuries of exposure. Here on Earth, we are protected from cosmic rays by two overlapping shields: Earth's magnetic field, which deflects the charged particles around the planet, and Earth's atmosphere, equivalent to roughly 10 meters of water in terms of radiation shielding. Between them, these two shields reduce the cosmic ray dose at Earth's surface to approximately 2 to 3 millisieverts per year, well within the range that human biology can tolerate without immediate consequence, though epidemiological studies suggest there is no truly safe threshold for ionizing radiation. Astronauts on the International Space Station, orbiting above most of the atmosphere but still within Earth's magnetic field, receive doses of approximately 100 to 200 millisieverts per year, enough that long-duration missions must be carefully managed and career radiation limits are strictly tracked. NASA currently sets a lifetime radiation limit for astronauts of between 600 and 1,200 millisieverts, depending on age and sex, a number calibrated to keep the increased cancer risk from radiation exposure below a 3% threshold above baseline. These limits are tight. 6 months on the ISS uses up roughly 80 millisieverts, a measurable fraction of the career allowance. Beyond the ISS, beyond the protection of Earth's magnetic field, in the deep interstellar space through which a Proxima-bound spacecraft would travel for years or decades, the galactic cosmic ray flux rises dramatically. Current estimates from instruments aboard Voyager 1 and 2, the New Horizons probe, and models of the interstellar radiation environment suggest that a spacecraft in the interstellar medium beyond the heliopause would receive roughly 400 to 900 millisieverts per year in cosmic ray exposure alone, depending on the phase of the solar cycle, which modulates galactic cosmic ray intensity even in deep space, and on the specific trajectory and shielding configuration of the spacecraft. Over a 20-year journey at 20% of light speed, this would amount to a total exposure of between 8,000 and 18,000 millisieverts, 8 to 18 times NASA's current maximum career limit. Over a 40-year journey at 10% of light speed, the numbers roughly double. The biological consequences of this level of exposure are severe, and they do not manifest only as cancer risk, though cancer risk is itself a serious concern. Cosmic rays cause direct damage to DNA through ionization, creating double-strand breaks in the double helix that the cell's repair machinery must fix correctly every time, or risk creating mutations that lead to malignancy. At low doses and low dose rates, the body's repair systems handle this reasonably well. At the dose rates projected for deep interstellar space over decades, the cumulative burden of DNA damage would likely overwhelm repair mechanisms. Studies on rodents exposed to high-energy heavy ion radiation, the most biologically damaging component of the galactic cosmic ray spectrum, have shown accelerated neurological aging, impaired cognition, and increased anxiety-like behaviour, in addition to the expected elevation of cancer risk. In the human brain, which is especially vulnerable to heavy ion bombardment, the long-term effects are among the least well-characterised and most concerning aspects of deep space biology. But cosmic rays are not the only radiation hazard. Beyond the heliosphere, the protective bubble of plasma and magnetic field that the Sun inflates around the inner solar system, extending to roughly 120 astronomical units before giving way to true interstellar space. A spacecraft would also be exposed to the stellar wind and radiation environment of any destination star during approach and arrival. For a mission to Proxima Centauri, this introduces what can only be described as the flare problem, and it is arguably the most dramatic threat on the entire list. Proxima Centauri is a flare star of the first order. Red dwarf stars like Proxima have a structural property that makes them systematically more prone to violent magnetic activity than Sun-like stars. Because they are fully convective, the entire star from core to surface participates in a churning, roiling circulation of plasma, rather than having the layered structure of a Sun-like star. Their magnetic fields are generated through a different mechanism, one that tends to produce intense, tangled, rapidly changing field configurations. These field configurations release their energy in flares, sudden, violent eruptions of magnetic energy that blast the star's surrounding space with X-rays, ultraviolet radiation, and charged particles. The Sun flares too, of course. But the Sun's flares are occasional events, typically separated by days or weeks, and they are released from a star bright enough that the flare energy represents a small percentage increase in total output. Proxima Centauri flares multiple times per day, and because Proxima is so intrinsically faint, remember, 0.007 times the Sun's luminosity, when it flares, the relative increase in radiation output is enormous. In 2016, astronomers using the Everyscope telescope network recorded what they classified as a superflare from Proxima Centauri, an event during which the star temporarily brightened by a factor of 68 in the UV band alone, producing approximately 100 times the ultraviolet radiation intensity required to kill even UV-hardy microorganisms on any nearby planet's surface. This superflare lasted only about 2 minutes. The ultraviolet output during those 2 minutes was catastrophic by any biological standard. Then, in 2019, a team analysing data from multiple observatories recorded another Proxima superflare, this one producing a rapid spike in UV emission of extraordinary intensity, reaching UV fluxes at Proxima B's orbital distance that were lethal on a timescale of seconds. Not minutes, seconds. The 2019 event was detected across multiple wavelengths simultaneously, optical, ultraviolet, and X-ray. confirming that these events are not instrumental artifacts but real eruptions of tremendous energy. The implications for habitability are, on the one hand, grim, and on the other hand, more nuanced than the headlines suggest. We will return to those implications in detail when we consider what an arriving crew would actually find. But for the ship in transit, the concern is different. A spacecraft approaching Proxima Centauri from the interstellar medium would begin entering the star's radiation environment months before arrival. Any biological crew aboard would need to be shielded from this radiation, and shielding adds mass, and mass is the mortal enemy of propulsion. This is one of the many places where the different problems of interstellar travel are not independent, but coupled. Solving one makes another harder. The shielding question has no consensus answer. Water is an excellent radiation absorber, and the idea of surrounding crew quarters with a water jacket, letting the ship's own life support reserves double as a radiation shield, has been discussed for Mars missions and could in principle be scaled to interstellar contexts. Polyethylene, a hydrogen-rich plastic, is another option. Laboratory tests have confirmed its effectiveness against the proton component of galactic cosmic rays. Active magnetic shielding, using superconducting coils to create a miniature magnetosphere around the ship, has been studied theoretically and would be effective against charged particles. Generating and maintaining the required field strength over years or decades of operation remains a formidable engineering challenge. The deepest problem with radiation shielding is that the most biologically damaging component of the galactic cosmic ray spectrum, the heavy ion component, particularly ion nuclei, is also the hardest to stop. Heavy ions are both more ionizing than protons, meaning they deposit more energy per unit of tissue traversed, and more penetrating, meaning they require more material to absorb. When a heavy ion cosmic ray nucleus passes through a shielded wall and into human tissue, it leaves a narrow trail of devastation at the cellular level, damaging or destroying cells in a cylinder, perhaps a micrometer wide but extending millimeters into tissue. The secondary particles created when the heavy ion collides with shielding material, a shower of protons, neutrons, and lighter nuclei, can actually spread the damage over a larger volume. In some configurations, adding more shielding makes things worse, not better. This is sometimes called the shielding paradox, and it is one of the most counterintuitive and genuinely troubling facts in the entire field of space radiation biology. And this is before we have even discussed the dust. The interstellar medium contains dust grains, particles of silicate, carbon and ice, typically ranging in size from a few nanometers to a few micrometers, present at a density of roughly 1 grain per million cubic meters on average. At low velocities, dust grains are irrelevant. A spacecraft moving at Voyager 1's speed would impact an interstellar dust grain and feel approximately the same effect as a bullet hitting a feather. The feather barely moves. Relativistic mechanics transforms dust particles into weapons at 10% of the speed of light, 30 Susan kilometers per second. A dust grain with a mass of 1 microgram carries a kinetic energy of approximately 450 megajoules. That is the explosive energy of roughly 100 kilograms of TNT, delivered by a particle you cannot see with the naked eye, striking the hull of your spacecraft at a rate proportional to the velocity of travel. At 20% of light speed, the energy scales with the square of velocity, making each impact 4 times more energetic still. Over years of travel through the interstellar medium, the cumulative effect of dust grain impacts on the leading face of a spacecraft hull would be erosion, pitting, and potentially catastrophic puncture, depending on the size of the grains encountered. The average density of the interstellar medium provides some comfort. The probability of striking a large grain in a given year of travel is low, but the expected number of impacts rises directly with velocity and travel duration, and the tail risk, the chance of encountering an unusually large grain or a region of locally elevated dust density, is non-zero and grows with the length of the journey. Mission designers have proposed protecting interstellar spacecraft with a sacrificial ablative shield on the forward face. a thick layer of material that absorbs the energy of grain impacts by vaporizing and ablating away, like the heat shield of a returning capsule. The mathematics suggest this approach could work for the expected grain sizes in the diffuse interstellar medium, but it adds mass. Everything adds mass. The propulsion budget bleeds for every added kilogram of protection. There is also a hazard that sounds almost whimsical until you consider the numbers. Hydrogen atoms, the most abundant atoms in the universe, exist in the interstellar medium at roughly 1 per cubic centimetre. At 20% of the speed of light, these atoms are not drifting gently past the ship. From the ship's perspective, they are arriving as a continuous beam of proton radiation, each hydrogen nucleus carrying kinetic energy proportional to the ship's velocity. At 20% light speed, the effective radiation dose from hydrogen atom impacts alone would be lethal to unshielded biological tissue in a matter of hours. A crew would need to be shielded from the interstellar hydrogen itself, not just from the cosmic ray component, but from the very medium through which they were moving. The more carefully you examine the interstellar medium, the more hostile it becomes. And none of this analysis has yet addressed the effects of years or decades of microgravity on the human body, which turns out to have its own staggering catalogue of consequences. Scott Kelly spent 340 consecutive days aboard the International Space Station between 2015 and 2016, the longest single spaceflight in American history at that time. His twin brother Mark, also an astronaut, remained on Earth throughout as a genetic control subject. When Scott returned, the NASA Twin study, which ran for years afterward, analysing biological samples collected before, during, and after the mission, produced results that genuinely surprised the scientists involved. Scott's telomeres, the protective caps at the ends of chromosomes, which normally shorten with age, actually lengthened during spaceflight, only to shorten rapidly upon his return to Earth. His gene expression profile changed, with thousands of genes showing altered activity levels. His gut microbiome shifted significantly in composition. His cognitive performance showed measurable declines in some areas. His retinal thickness changed. His carotid artery walls thickened. His immune system showed altered response profiles. I will admit that when I first read the full summary of the twins' study findings, I had to sit with it for a moment, not because any single finding was catastrophic. Most of Scott's biological parameters returned approximately to baseline within 6 months of his return to Earth. But because the sheer breadth of the changes across so many different biological systems simultaneously told a very clear story about what the human body is doing in space. It is continuously adapting, in ways both visible and invisible, to an environment it was never designed for. Some of those adaptations are benign or even beneficial, others are not. And the critical question for interstellar travel is, what happens when that adaptation process runs not for 340 days but for 40 years, or 400 years? Bone density loss in microgravity runs at approximately 1 to 1.5% per month in weight-bearing bones without countermeasures. That rate can be slowed significantly by intensive exercise. Current ISS protocols require astronauts to exercise for about 2 hours daily, specifically to counteract bone and muscle loss, but it cannot be entirely stopped. Over the duration of a typical 6-month ISS mission, astronauts lose roughly 10 to 15% of bone density in the lumbar spine and hips if their exercise protocols are suboptimal, and even with optimal protocols, some loss occurs on a 20-year interstellar journey in microgravity. Assuming the spacecraft could not rotate to provide artificial gravity, which requires large radius, structural complexity, and engineering weight that a propulsion-optimized vessel might not afford, the accumulated bone and muscle loss would be catastrophic. A crew arriving at Proxima Centauri after 20 years in microgravity might be physically incapable of performing the basic physical tasks required to operate the spacecraft, conduct surface operations, or respond to emergencies. The solution to microgravity is rotating the spacecraft, creating centrifugal force that mimics gravity by spinning a section of the ship. Arthur C. Clarke imagined this in 1968. The rotating habitat of the Discovery in 2001, A Space Odyssey, is perhaps the most famous depiction of the concept. The engineering requirements are real but not fantastical. The key variables are the radius of rotation, the rotation rate, and the desired gravitational equivalent. To produce 1g equivalent acceleration at a radius of 100 meters requires a rotation rate of approximately 3 revolutions per minute, slow enough not to cause the vestibular disruption that faster rotation induces. A 100-meter rotating habitat is large by current standards, but is not obviously impossible for a mission with the propulsion budget to travel to another star. But again, mass. Rotating habitat sections add structural complexity, mass, and potential failure modes. Every kilogram of habitat is a kilogram not devoted to propulsion, fuel, life support instruments, or redundancy systems. The engineering of an interstellar crewed spacecraft is not the sequential solving of individual problems. It is the simultaneous juggling of dozens of coupled constraints, each of which imposes costs that affect all the others. This is the architecture of difficulty that surrounds the journey to Proxima Centauri, and we have not yet discussed the aspect of the problem that, to my mind, deserves more attention than it typically receives in the technical literature: what the journey does to the human mind. There is a thought experiment that mission psychologists sometimes use when trying to communicate the psychological conditions of long-duration spaceflight to people who have never experienced it. Imagine you are in a room about the size of a large apartment. The room contains everything you need to survive: food, water, air, light, a bed, exercise equipment, a workstation. There are perhaps 5 or 6 other people in the room with you. You cannot leave. You cannot meaningfully change the room's dimensions, decor, or sensory environment. You cannot go for a walk, cannot feel wind or rain, cannot smell grass or soil, cannot step into a space that is not defined by the same walls, the same floors, the same ceiling that enclosed you yesterday and will enclose you tomorrow. Outside the room, there is nothing, not the silence of a forest at night, but a vacuum so complete and so hostile that exposure to it for 30 seconds would kill you. The nearest human beings outside your group are years away at the speed of light. No communication you send will receive a reply in less than 8 years round trip. You are, in every meaningful sense, more alone than any human being in history has ever been. Now extend this scenario from 6 months, the longest continuous crewed spaceflight currently practiced with regularity, to 20 years. The psychological challenges of long-duration spaceflight are well documented even for missions measured in months. NASA identifies 6 core behavioral health risks for astronauts in isolated, confined, extreme environments: cognitive decline, psychiatric disorders, interpersonal conflicts, loss of teamwork and communication, displacement of cultural and social identity, and, perhaps most practically urgent, the erosion of the crew-to-ground relationship as the mission progresses. This last factor, sometimes called the third quarter phenomenon, was first observed in studies of Antarctic winter-over crews and subsequently confirmed in spaceflight analogue studies. A reliable dip in mood, motivation, and performance that tends to cluster around 3/4 of the way through a mission's expected duration, when the end is visible but still far away and the accumulated fatigue of confinement reaches its peak. In spaceflight itself, the evidence is unambiguous and sometimes alarming. Astronauts on long-duration ISS missions have reported hallucinations from sleep deprivation, episodes of profound disorientation, interpersonal conflicts severe enough to require intervention from mission control, and periods of emotional flatness, a withdrawal of affect from the surrounding environment that bear clinical resemblance to depressive episodes. The confined, isolated, monotonous character of spaceflight strips away most of the psychological inputs, the novelty, the social variety, the environmental change that healthy human functioning depends on. What remains is a relentless sameness that compounds over months into something psychologically corrosive. But here is the dimension that has no analogue in current spaceflight research, and that makes interstellar crewed missions categorically different from anything we have studied. The communication delay. Right now, an astronaut on the ISS can have a real-time conversation with family members on Earth, with a delay measured in fractions of a second. They can watch the news as it happens. They can maintain continuous emotional connection to the world they left, even on a crewed Mars mission, which currently represents the outer edge of planned human spaceflight. Communication delays range from roughly 3 minutes to 22 minutes one way, depending on the relative positions of Earth and Mars in their orbits. A delay of 22 minutes is inconvenient. It changes the nature of communication, but it does not destroy it. You can still have a conversation in the same day. You can still feel connected. At Proxima Centauri's distance, 4.24 light-years, the one-way communication delay is 4.24 years. 4 years and 3 months approximately for a signal moving at the speed of light. A round-trip exchange, "How are you?" and the reply, "I am fine, thank you," takes more than 8.5 years. No real conversation is possible. There is no real-time connection to Earth, to family, to culture, to the accumulating experience of humanity. A crew bound for Proxima Centauri on a 20-year voyage at 20% light speed would send messages home during the outbound journey, knowing that no reply could reach them before their arrival. The entire communicative relationship with Earth would be asynchronous, time-shifted, one-directional in any meaningful practical sense. It would feel less like staying in touch and more like writing letters to people who would be very old or dead before the letters arrived. The compounding psychological weight of this isolation, not just physical isolation from other humans, but temporal isolation from the flow of human experience, history, and relationship, is something that no analog study has fully examined, because no analog study has been able to replicate it. Antarctic winter-over crews are isolated for months, not decades, and they can maintain real-time communication. Submarine crews are isolated for months in cramped quarters, and they can communicate in real time. Prison populations have served decades of social isolation, but with ongoing ambient connection to the social world. Visitation, news, the knowledge that other people are living their lives in continuous relationship with you, even if you cannot join them. An interstellar crew would have none of this. They would be the loneliest human beings who ever lived, by any reasonable metric of loneliness, and they would be expected, over the course of this extreme isolation, to maintain technical competence, make complex engineering and scientific decisions, sustain interpersonal relationships under extraordinary pressure, preserve their psychological health, without the social resources that human psychological health depends on, and ultimately, if the mission succeeded, arrive at their destination ready to do the most important scientific work in human history. Whether human beings can do this is not a question with a comfortable answer, and the question becomes considerably more uncomfortable when you extend the journey duration beyond one human lifetime, because at lower propulsion velocities, which remain the only kind achievable by any near-term technology, the journey to Proxima Centauri does not fit inside a single human life. At 5% of light speed, the journey takes approximately 84 years. At 3% of light speed, approximately 141 years. At 1% of light speed, 3,000 kilometers per second, which itself represents a velocity approximately 176 times faster than Voyager 1. The journey would take 424 years. These are generation ship timescales, missions where the people who arrive at Proxima Centauri are not the people who departed Earth, but their descendants, many generations removed. The generation ship concept introduces an entirely different category of problem, one that blurs the boundary between engineering and ethics. The people born aboard an interstellar generation ship did not choose to live their entire lives in a spacecraft. They did not choose the mission. They cannot leave. They are committed, by the decisions of their ancestors, to a purpose they may or may not share, a destination they may never see, and a set of constraints, physical, social, genetic, that no other human beings in history have faced. The ethics of the generation ship are genuinely unresolved, and they are not merely abstract. If we ever actually build one, the ethical weight of that decision to conscript future generations into a mission they did not choose, will land on the designers and the funders with a force that no philosophical framework has yet fully reckoned with. Then there is the mathematics of genetic diversity, which makes the problem concrete in ways that ethics sometimes cannot. A breeding population needs a minimum number of unrelated individuals to maintain genetic diversity over many generations, without the compounding of harmful recessive alleles that comes from inbreeding. Estimates of the minimum viable population for a multi-century voyage vary considerably, from roughly 160 individuals as an absolute floor to several thousand for robust long-term health. And these numbers have direct implications for the size of the ship, the mass of the life support systems, the fuel budget, and therefore the achievable velocity. The minimum viable population for a generation ship is not a rounding error in the calculation. It is a fundamental constraint that shapes every other aspect of the mission design. There is one technology that could, in principle, cut through all of these human factors problems with a single elegant stroke: suspended animation or biostasis. If crew members could be placed in a state of dramatically reduced metabolism, a kind of induced hibernation, with body temperature lowered, cellular processes slowed, and the biological clock of aging essentially paused for the duration of the voyage, the journey would feel far shorter in biological terms, and the psychological, social, and nutritional requirements of the crew would be reduced by orders of magnitude. Some mammals hibernate naturally. Bears reduce their metabolic rate by roughly 25% during winter sleep, which is impressive but nowhere near the 90% or greater reduction that would make human biostasis practical for a multi-decade voyage. Certain organisms, nematode worms, tardigrades, some vertebrate species, can enter states of cryptobiosis that are metabolically close to a rest. The question of whether human biology, with its extraordinary cellular complexity and its continuous requirement for regulated gene expression and protein turnover, can be safely paused and reliably restarted after years or decades remains genuinely open. Research continues, but as of now, human biostasis is a concept for which we have promising biological analogies and essentially no practical implementation. The body, the mind, the social fabric of a crew, all of them face challenges on an interstellar voyage that dwarf anything in our current experience of human spaceflight. And this is before the crew arrives, because what they would find at Proxima Centauri is, in its own way, the most surprising chapter of all. In the summer of 2016, an astronomer named Guillaume Anglada-Escudé was standing at the threshold of an announcement that he had spent years trying to avoid making prematurely. Anglada-Escudé was born in Catalonia and trained in astrophysics with a particular focus on low-mass stars and the planets that might orbit them. He had worked at institutions in Germany, the United States, and the United Kingdom, and his work on the radial velocity method, the technique of detecting planets by measuring the microscopic back and forth motion they induce in their parent star, had given him an intimate familiarity with the particular kind of uncertainty that haunts exoplanet science. The radial velocity method is extraordinarily sensitive. It can detect a planet by measuring Doppler shifts in the star's light amounting to a few meters per second, the walking speed of a brisk pedestrian as a fraction of the velocity of light. But it is also susceptible to false positives, to instrumental systematics, to stellar activity that mimics the signature of a planet. Red dwarf stars like Proxima Centauri are notorious for this. Their surfaces see with magnetic activity, star spots, plages, granulation and flares that create complex Doppler noise in the stellar spectrum, noise that can look, to the unwary or the hopeful, exactly like a planetary signal. Finding a genuine planet around a red dwarf is a process of painstaking disentanglement, separating the stellar noise from the orbital signal, accumulating enough data to distinguish the periodic wobble of a planet's gravity from the quasi-periodic variability of the star's rotation, and convincing yourself, and then your colleagues, and then the community, that what you are seeing is real. Anglada-Escudé and his team had been observing Proxima Centauri intensively since 2013. as part of a program he called Pale Red Dot, a deliberate echo of Carl Sagan's Pale Blue Dot, the famous photograph of Earth taken by Voyager 1 from 6 billion kilometers away in 1990, in which our planet appears as a tiny, fragile speck suspended in a beam of sunlight. The observation campaign accelerated in January 2016 with daily measurements at multiple telescopes coordinated across multiple continents. The European Southern Observatory's HARP spectrograph in Chile, the UVES spectrograph on the Very Large Telescope, and contributed data from several other instruments. For months, the data accumulated. For months, the team watched the signal strengthen. Proxima Centauri was wobbling, not by much. The radial velocity semi-amplitude of the signal was only about 1.38 meters per second, less than the running speed of a slow jogger. But it was wobbling with a period of 11.186 days, consistently, in every dataset across every instrument. The signal persisted through different observing seasons. It survived statistical tests designed to expose stellar activity contamination. It emerged from the noise with a false alarm probability estimated at roughly 1.5 times 10^7, about 1 chance in 7 million that the signal was a statistical artifact rather than a real planetary orbit. But Anglada Escudé did not announce this in January. He did not announce it in February or March, even as the data grew more compelling with each passing week. The reason is both professional and deeply human. He had been fooled before. Not personally exactly, but the field had been fooled, repeatedly, painfully, in ways that left permanent scars on the credibility of exoplanet science. Gliese 581G, a planet around a nearby red dwarf announced in 2010 to enormous excitement, had been called into question almost immediately and has never been reliably confirmed. Alpha Centauri b, announced in 2012 as the nearest exoplanet to our Sun, was subsequently shown to be a statistical artifact, a false positive created by an overfitting of the data. The graveyard of once celebrated exoplanet discoveries is long, and the headstones are carved from the reputations of careful, intelligent scientists who believed the data a little too readily, so Anglada Escudé kept looking. He accumulated more data. He ran more tests. He pushed the analysis further and further, looking for the flaw, looking for the asterisk, looking for the reason to walk away. And the signal refused to go away. It stayed, it strengthened, it held up against every test. He finally submitted the paper to Nature in the summer of 2016. It was published on the 24th of August 2016, with the title, A Terrestrial Planet Candidate in a Temperate Orbit Around Proxima Centauri. The paper carried 18 co-authors. The accompanying press conference at the ESO headquarters in Garching, Germany, drew an audience that was by the standards of academic astronomy enormous, and the headlines that followed were by any standard extraordinary. The Guardian, Discovery of Earth-like planet Proxima b raises hopes for life. The New York Times, 1 star over, a planet that might be another Earth, Nature itself. Earth-sized planet around nearby star is astronomy's dream come true. I find myself moved by this moment every time I revisit it, not because of the press coverage, which was predictably breathless, and predictably hedged by the might be and could be that science reporters lean on when they want to convey excitement without making promises. What moves me is the image of Anglada Escudé himself, who had spent years approaching this data with the deliberate skepticism of a scientist who has learned the cost of believing too easily, finally arriving at the place where the evidence simply would not let him disbelieve any longer. He did not rush to be first. He did not rush to be celebrated. He waited until the signal was undeniable, and then he stood in front of the cameras and said, "There is a planet. It is real. It is there. This is what science looks like from the inside." Not a dramatic eureka moment, but years of methodical accumulation and careful denial, ending not with certainty. Nothing in empirical science ends with certainty, but with a confidence that has earned its own weight. The discovery of Proxima b transformed the conversation about interstellar travel from the purely theoretical to the urgently practical. There had always been reasons, in principle, to send a probe or a crew to Proxima Centauri. It was the nearest star. understanding our nearest stellar neighbourhood, was a legitimate scientific goal independent of whether any planets were present. But the existence of a rocky, Earth-mass planet in the habitable zone changed the emotional character of the goal. It gave the mission a specific address. It gave the question a specific answer to seek. It said, in effect, this is not merely about exploring the nearest star. This is about asking whether life has found a second foothold in the nearest star system. And if the answer is yes, even if the life is microbial, even if it is a smear of chemistry on a wind-scoured rock, then everything changes, everything changes. The phrase sounds like hyperbole. It is not. The detection of life beyond Earth, any life, anywhere, at any level of complexity, would represent the most significant scientific discovery in the history of our species. It would answer, with data rather than speculation, the question of whether life is a singular accident of Earth's particular history or a general consequence of the right physical and chemical conditions. It would transform astrobiology from a discipline that studies the potential for life elsewhere to a discipline that studies life elsewhere as a fact. It would ripple through philosophy, religion, politics, and culture with a force that no other scientific discovery has matched. The Copernican revolution, the Darwinian revolution, the quantum revolution. All of these changed our understanding of where we are and what we are made of. The discovery of extraterrestrial life would change our understanding of whether we are alone, and the weight of that change is, I think, difficult to overestimate. This is why the journey to Proxima Centauri is not just an engineering challenge. It is a philosophical mission. It is the species asking the deepest question it knows how to ask. And then, in April 2019, something happened that added a layer of strangeness to the question that nobody had quite anticipated. The Breakthrough Listen project, the most well-funded and technically sophisticated SETI program in history, was conducting observations of Proxima Centauri using the Parkes Muiryang radio telescope in Australia. The observations were routine. Proxima is a high-value SETI target simply by virtue of being the nearest star, and Breakthrough Listen monitors it periodically as a matter of course. But in the data from observations conducted on the 29th of April 2019, a student researcher named Shane Smith, working through the archival data 2 years later in 2020, found something he could not immediately explain: a narrowband radio signal, 982.002 MHz, drifting slightly in frequency over time, as a transmitter on the surface of a moving object would be expected to drift due to the Doppler effect of the object's rotation, arriving from a direction consistent with Proxima Centauri's position on the sky. Present in 2 separate observing sessions separated by several hours, but absent in the observations in between, as would be expected for a source that was below the horizon for part of the time, the signal was designated BLC-1, Breakthrough Listen Candidate 1. And for a brief charged period of weeks, it was the most discussed piece of data in the world of SETI. I want to be precise about what BLC-1 was and what it was not. It was a real signal, a genuine pattern in the data, not an instrumental noise floor artifact, not a simple calibration error. It was narrowband in frequency, which is a characteristic that distinguishes artificial transmitters from naturally occurring astrophysical sources, which tend to be broadband or to emit at specific spectral lines associated with atomic transitions. Its frequency drift was consistent with a rotating planetary surface source, or at least was not inconsistent with one, and it came from the direction of the nearest star to our Sun, which happened to be the star around which an Earth-mass planet in the habitable zone had just been discovered. It was also, as subsequent analysis by the Breakthrough Listen team made clear, almost certainly a signal of terrestrial origin. Radio frequency interference from human technology on Earth, perhaps reflected or propagated in an unexpected way, mimicking some of the characteristics that would be expected from an extraterrestrial source. The detailed analysis, published in Nature Astronomy in 2021 under the lead authorship of Sophia Sheikh, identified multiple features of BLC-1 that were inconsistent with an astrophysical origin, including the signal's failure to appear consistently in all the data channels where it should have been visible if it were truly emanating from outside the terrestrial environment. The conclusion: BLC-1 was not a message from Proxima Centauri, but the episode illuminated something important. The nearest star to our Sun, the one with a planet in its habitable zone, the one that Guillaume Anglada Escudé spent years watching wobble, is the place where, if you found a signal, the rest of the world would immediately understand why it mattered. Proxima Centauri is not just a scientific target. It has become a cultural symbol of the question that humanity most deeply wants answered. Whether the answer waiting at Proxima is science, or chemistry, or something that no category we currently possess is adequate to describe, we will not know until we look, and looking, in any truly meaningful sense, means going. There is one aspect of the journey to Proxima Centauri that surpasses every other in its philosophical strangeness, in the way it destabilizes intuition and forces the mind into territory where common sense becomes a liability. It is the matter of time. Einstein's special theory of relativity, published in 1905, makes a prediction that every student of physics learns but that almost no one fully feels until they push on it hard. Moving clocks run slow, not metaphorically slow, not approximately slow. Actually, measurably, physically slow, from the perspective of a stationary observer, by a factor that depends on the velocity of the clock relative to the observer. This phenomenon is called time dilation, and it is not a quirk of specific types of clocks or specific measuring instruments. It applies to all physical processes, including the biological processes that constitute aging, cognition, and life. The mathematical heart of time dilation is the Lorentz factor, denoted by the Greek letter gamma, defined as gamma1 minus c2v21, where v is the velocity of the moving object and c is the speed of light, when v is much smaller than c, as it is for all everyday velocities, and even for the velocities of current spacecraft. The denominator is very close to 1, and gamma is very close to 1, and time dilation is negligible. But as v approaches c, the denominator approaches 0, and time dilation becomes extreme. At 99% of the speed of light, gamma approximately 7.9, meaning that 1 year aboard the moving spacecraft corresponds to approximately 7.09 years on Earth. At 99.9% of the speed of light, gamma approximately equals 22.4 for breakthrough Starshot's proposed 20% of light speed, v0, 2c. The Lorentz factor is gamma 1 minus 0.041, Einbeights 1.021 at 0.2c. Time dilation is modest. The ship's clocks would run approximately 2.1% slower than Earth's clocks. Over a 20-year journey as measured from Earth, the crew would experience approximately 19.6 years, a difference of only a few months. This is real and measurable, but it is not the kind of dramatic time dilation that makes the thought experiment truly arresting. The truly arresting case is constant acceleration. Imagine a spacecraft that could maintain a constant acceleration of 1g, 9.8 meters per second squared, the same as Earth's gravitational field at the surface, throughout the entire journey. Such a ship would have two enormous practical advantages. First, the occupants would feel a gravitational force equivalent to Earth normal, eliminating the bone density, muscle atrophy, and fluid shift problems of microgravity. Second, the velocity would increase continuously throughout the accelerating phase, and the spacecraft would reach a significant fraction of light speed by the midpoint of the journey. The mathematics of constant acceleration relativistic travel have been worked out in detail, and the numbers are extraordinary. For a journey to Proxima Centauri at constant 1g acceleration to the midpoint, then constant 1g deceleration to arrival, an observer on Earth would measure a total travel time of approximately 3.5 years. The crew aboard the ship, however, would experience approximately 2 years of proper time, the time measured by their own clocks, their own aging, their own biological processes. The time dilation is not enormous at these speeds, but it is real. Now extend the thought experiment. At constant 1g acceleration and deceleration, a ship could reach the centre of the Milky Way, approximately 26,000 light-years away, in about 21 years of crew time. while roughly 26,000 years passed on Earth. A journey to the Andromeda Galaxy, 2.537 million light-years away, would take approximately 29 years of crew time, while more than 2.5 million years elapsed on Earth. The crew would return, if they could, to a solar system that, depending on the duration of their journey, might no longer resemble the one they left. Our Sun will leave the main seeks in roughly 5 billion years. A ship crew that travelled to Andromeda and back at 1G would return to find the Sun a red giant. This is, of course, a thought experiment limited by the energy requirements. Maintaining 1G acceleration all the way to relativistic velocities requires energies that dwarf anything in human experience or any plausible near-future energy budget. But the thought experiment is not idle speculation. It is a demonstration of what the physics of Einstein's universe allows, in principle, for a sufficiently energetic civilization. For Proxima Centauri specifically, the time dilation question has a particular poignancy, even at 20% of light speed. The breakthrough Starshot target velocity for its nanocraft. The probe itself is barely aging relative to Earth, but if you were to extend the crude mission scenario and gradually push the velocity higher, you would reach a threshold where the time dilation becomes personally consequential. At 50% of light speed, v0.5c gamma approximately equals 155, and a journey of 4.24 light-years in Earth time takes about 3.67 years in crew time. The difference is real but modest. At 86.6% of light speed, v.866c, gamma 2.0 exactly, and the crew ages at half the rate of Earth observers. The 4.24 light-year journey takes 2.12 years of crew time, while 4.24 years pass on Earth. What this means in practice is the following. A crew launched on a relativistic journey to Proxima Centauri could, in principle, age less during the voyage than the people they left behind on Earth. They could set off while young, arrive middle-aged, and return. If a return were possible, which it largely is not given the propulsion requirements, to find that Earth had aged far more than they had. Their children would be older than them. Their friends might be dead. The world they returned to would be a world they could understand intellectually. They would know, from their physics, exactly what to expect, but which they would experience emotionally as a profound dislocation. The mathematical universe is internally consistent. The human universe of attachment, memory and relationship is not equipped to process it. This dislocation is not hypothetical. It is a genuine psychological scenario that any crude relativistic mission would need to reckon with. And the faster the mission, the more relativistic the travel, the more severe the dislocation becomes. At high enough velocities, the crew members would effectively be travelling not just through space, but through time, arriving in a future that they did not inhabit step by step, but leap to in a single bound. Every person who cared about them on Earth would be gone. Every institution they identified with would have evolved beyond recognition. Every cultural reference point they carried in their memories would belong to the historical past. This is not a problem that can be solved with therapy or preparation. It is a categorical feature of relativistic travel, baked into the geometry of space-time itself. It changes the nature of the mission from an expedition, a departure and return, into something closer to an emigration, a one-way journey into a future that no current living human will share. There is a question that physicists sometimes use to illustrate the strangeness of this situation, and it is worth pausing on it. From whose perspective does the journey take 20 years? The answer is deceptively simple and actually profound. From Earth's perspective, the ship travels 4.24 light-years at 20% of light speed in 21, 2 Earth years, accounting for the slight adjustments from special relativity. From the ship's perspective, the proper time experienced by the crew is slightly shorter, approximately 20.8 years at this modest gamma factor. Both are correct. Both are real. Space-time does not have a single correct clock. It has a family of clocks, all running at different rates depending on their relative motion, all equally valid in the mathematical formalism of relativity, and all measuring genuinely different quantities. The crew's 20.8 years are not really 21.2 Earth years, slowed by some external process. They are 20, 8 years, experienced as 20.8 years in every biological, psychological and physical sense, while simultaneously in another equally valid reference frame, 21.2 years elapse. This is not paradox, it is precisely what relativity predicts and what experiments with atomic clocks have confirmed repeatedly at lower velocities since 1971, but the human reality of it remains startling. The universe does not keep a universal clock. Every observer carries their own time, and the faster you move, the further your time diverges from the time of those who stay behind. Now, add to this the stakes that the mission carries, and you begin to feel the full weight of the undertaking. We're not simply talking about the technical challenge of building a propulsion system and a radiation shield and a rotating habitat. We are talking about sending human beings, specific human beings, with names and families and histories and futures, on a journey that will transform them in ways we cannot fully predict, at velocities that will separate them from the rest of humanity, not just in space but in time, to a destination where the most important question in the history of science may have an answer waiting. The civilizational stakes of the journey to Proxima Centauri are not secondary to the technical challenges. They are the reason the technical challenges must be overcome. And those stakes have grown in the decades since Anglada Escudet's paper with every new discovery about what the Proxima system actually contains, and what those contents tell us about the odds of finding life there. Let us arrive. We are going to imagine for the duration of this chapter that the propulsion problem has been solved, that some future iteration of human technology or human civilization has produced a spacecraft capable of reaching Proxima Centauri in a humanly meaningful time frame. The journey is behind us, the deceleration is complete. We are in the Proxima system, in orbit, our instruments trained on the planet designated Proxima Centauri b. What do we see? Begin with what we know, and be honest about how much of what we know is inference layered upon inference. Model stacked on model, educated guess treated as established fact by the momentum of popular science writing. The physical bedrock is this: a planet exists, with a minimum mass of 1.55 Earth masses, orbiting Proxima Centauri at 0.04856 astronomical units, roughly 7.26 million kilometers, with a period of 11.186 days. We know this because the star wobbles. We know the wobble is periodic. We know the mass and orbital parameters from the amplitude and period of the wobble. We do not know the planet's radius. We do not know its density. We do not know its composition. We do not know whether it has an atmosphere, and if so, what it is made of. We do not know whether its surface is solid or liquid or gaseous. We do not know whether it has a magnetic field, or water, or any chemistry that we would recognize as consistent with the kind of life we are familiar with. Everything beyond the orbital parameters is, to varying degrees, modelled inference. The models are based on plausible physical assumptions and the best available comparative planetology, and some conclusions they generate are highly probable, but highly probable is not the same as known. With that caveat firmly in place, let us walk through what the models tell us, because the picture that emerges is genuinely extraordinary in its strangeness. The first and most dramatic feature of Proxima b's probable environment is tidal locking, because the planet orbits so close to its star, roughly 0.05 AST compared to Mercury's 0.39 astronomically from our Sun. The gravitational gradient of the star across the planet's diameter is powerful enough to synchronize the planet's rotation with its orbital period. Just as Earth's gravity has locked the Moon so that the same face always points toward us, Proxima Centauri's gravity has almost certainly locked Proxima b so that one face permanently points toward the star, and the opposite face permanently faces the cold of deep space. The implications of this are profound and strange. The substellar point, the spot on the planet's surface directly beneath the star at all times, receives constant, unvarying stellar radiation equivalent to approximately 65% of the solar constant at Earth's surface. Despite Proxima being far dimmer than the Sun, the planet's proximity more than compensates. The stellar hemisphere of the planet experiences a perpetual reddish noon that never ends. The dim red glow of Proxima Centauri, hanging permanently at the zenith, neither rising nor setting, casting long red shadows in every direction from every object. The stellar hemisphere is warm enough, depending on the atmosphere, to potentially host liquid water. The anti-stellar hemisphere, the permanent night side, faces the void of deep space, with no direct stellar heating whatsoever. Without an atmosphere to redistribute heat from the day side, the night side would be a frozen, airless wasteland at temperatures approaching 100 Kelvin, cold enough to freeze carbon dioxide into dry ice and nitrogen into liquid. The terminator, the boundary between the day and night hemispheres, would be the only region of moderate temperature, a ring of perpetual twilight, where the temperature is neither roasting nor freezing, but potentially, tantalizingly, in the range where water might remain liquid. But an atmosphere changes everything. Climate models of tidally locked planets have evolved considerably in the past decade, and the consensus has shifted from early expectations of extreme day-night contrast toward a more moderate picture, provided the atmosphere is substantial enough. A thick atmosphere, Earth-like in composition and pressure, would efficiently transport heat from the day side to the night side through atmospheric circulation, dramatically reducing the temperature contrast between hemispheres. The day side would remain warmer, but not catastrophically so. The night side would remain cooler, but not frozen to absolute cold. The terminator region would widen into a broad zone of habitable conditions, and even the day and night sides might support liquid water at the surface if the atmospheric circulation were efficient enough. The critical question is whether Proxima b has an atmosphere at all, and this is where the flare problem re-enters the picture with devastating force. We established in an earlier chapter that Proxima Centauri is a prolific flare star. Let us now quantify what that means for a planet orbiting at 0.05 AStroMu. Earth orbits at 1 AStroMu from the Sun, 20 times farther than Proxima b orbits its star. The intensity of radiation falls off with the square of distance, which means that Proxima b receives radiation from its star at a flux that is, at a given star luminosity, 400 times more intense per unit of surface area than Earth receives from the Sun. But Proxima is much dimmer than the Sun, so the quiescent radiation environment is not actually 400 times more intense than Earth's. The combination of proximity and dimness leaves Proxima b with roughly 65% of Earth's total energy flux. In normal conditions, this is manageable. Flares are not normal conditions. During a superflare, the kind of event recorded in 2019 in which Proxima's brightness increased by a factor of tens in the UV band within seconds, Proxima b would receive a pulse of radiation orders of magnitude above anything Earth experiences, even during the most powerful solar events. The 2019 superflare produced UV fluxes at Proxima b's orbital distance that were estimated at approximately 100 times the lethal threshold for even the most UV-resistant microorganisms known. This was not a marginal exceedance of a biological threshold. It was a systematic, repeated obliteration of it, and these events are not rare. Studies of Proxima Centauri's flare frequency indicate that superflares of similar intensity to the 2016 and 2019 events occur multiple times per year. Smaller flares, still intense, still biologically significant, occur multiple times per day. Any unprotected surface life on Proxima b would be exposed to this radiation every single day, with major events recurring on timescales short compared to any evolutionary or geological process. But surface life is not the only possibility. Underground life, protected by meters of rock, would be immune to surface radiation. Oceanic life, shielded by meters of water, would similarly survive events that sterilize the surface. The question of atmospheric protection is more nuanced than it first appears. An atmosphere rich in ozone would absorb much of the UV flux from flares, just as Earth's ozone layer absorbs the Sun's ultraviolet radiation, but modelling by Asaf Segura, Antigona Segura, and others has shown that the repeated UV and X-ray bombardment of flares can, over years and decades, deplete the ozone layer of a planet like Proxima b by as much as 90%. The ozone depletes faster than it replenishes. A planet that starts with an Earth-like atmosphere might, over the course of stellar bombardment, lose most of its ozone shield and thereafter see its surface bathed in biologically lethal UV at all times. Not just during flares. There is also the stellar wind to consider. Red dwarf stars like Proxima generate stellar winds, streams of charged particles emanating from the corona that, while lower in mass flux than the Sun's wind, act on planets much closer to the star. The stellar wind pressure at Proxima B's orbit is estimated to be approximately 2,000 times the solar wind pressure at Earth's orbit. This enormous pressure has two effects. It can physically erode the planet's upper atmosphere over time, gradually stripping away lighter gases, and it confines or compresses any planetary magnetic field, reducing the area of the magnetosphere available to protect the planet. Studies suggest that even a Mars-like magnetic field, far weaker than Earth's, would be overwhelmed by Proxima's stellar wind, leaving the atmosphere largely unprotected against particle bombardment. Does Proxima B have a magnetic field? The answer depends on whether the planet has a metallic core that is still liquid, convecting, and generating a dynamo. For an Earth-like planet, this is normally expected, but Proxima B's tidal locking may complicate the picture. Tidal dissipation, the flexing and heating of the planet's interior by gravitational tides, could maintain sufficient heat to keep the core liquid and the dynamo active. Or it could have baked the interior too thoroughly, creating an overheated, geologically sluggish world without an active dynamo. The models disagree on this point, and the disagreement matters enormously for the habitability question. All of this leads to a picture of Proxima B that is, in its way, compelling evidence for the difficulty of life in a red dwarf system, and equally compelling evidence for the resilience of life once it gets a foothold, because every barrier to surface life that the Proxima system erects also selects for more robust, more adaptable, more radiation-resistant life. If life ever emerged on Proxima B, it did so in an environment far more hostile than the early Earth, and whatever survived and diversified was by definition tough. Extremophile life on Proxima B, if it exists, might be unlike anything we have encountered, even in Earth's most challenging environments. There is also the matter of what the planet's surface actually looks like. And here, the thought experiment of arrival becomes genuinely strange, because everything about the visual and physical experience of Proxima B would be disorienting to human senses. The star in the sky, directly overhead on the day side, never moving, never rising or setting, would appear roughly 3 times the angular diameter of our Sun as seen from Earth, despite being a much smaller star, simply because it is so much closer. Its colour would be a deep, ruddy orange-red, a fire-coal glow rather than the brilliant white-yellow of our Sun. The light on the day side of Proxima B would be a permanent red-tinted dusk, as if the sky were always at the hour before sunset. Photosynthetic life, if it existed, would need to absorb light at infrared wavelengths rather than visible wavelengths. One proposal suggests that plant analogues on Proxima B might be black in colour, absorbing as much of the limited visible light as possible, giving the landscape the appearance of a scorched, ink-dark plain beneath the red star. Stars would be visible during the day on the anti-stellar hemisphere in perpetual unfiltered night. The Alpha Centauri binary system, Proxima's gravitationally bound companions, would appear as 2 distinct bright stars, separated by a few arc minutes at their closest approach, the brightest pair in Proxima B's sky. A human standing on the anti-stellar surface of Proxima B and looking up at Alpha Centauri would be looking back toward the solar system, with the Sun appearing as just another moderately bright star in the background. Indistinguishable from thousands of others without a detailed star chart, the atmosphere, if any remains, if it has not been stripped by stellar wind and flares, would almost certainly be different in composition from Earth's. A planet that has spent billions of years in a very different radiation environment, with a very different geological history, would not be expected to have developed the same atmospheric chemistry as Earth. The presence of molecular oxygen in Earth's atmosphere is itself a biological signature, a product of billions of years of photosynthesis, which means that detecting oxygen in Proxima B's atmosphere would be strong evidence for life if we could detect it. But the flare activity of the star complicates even this signal. UV photolysis of water vapour in the upper atmosphere can produce abiotic oxygen through photochemical pathways, potentially mimicking the biological oxygen signature without life being involved. This is what astronomers call a false positive biosignature, and it is one of the deepest challenges in exoplanet science. The signals we are looking for, the chemical signatures of life in a planetary atmosphere, can, in some circumstances, be produced by non-biological chemistry. Disentangling the biological from the abiotic in a distant planet's spectrum, observed across light years through a telescope, is an exercise in ambiguity that the field is only beginning to develop the tools to address. And then there is the signal that arrived from Proxima Centauri in 2019, detected 2 years later, investigated carefully and judged almost certainly to be terrestrial radio frequency interference, BLC1. Almost certainly. The qualifier remains. No one has identified the specific Earth-based source. The analysis showed multiple inconsistencies with an astrophysical origin, but it did not produce a terrestrial source that matched all the signal's characteristics. The case was closed for practical purposes, for the purposes of the scientific community's continued function, because the alternative, that it was genuinely extraterrestrial, requires far more evidence than a single detection of a frequency that happens to be a common broadcast band for terrestrial technology. But it was not definitively closed. It was filed as almost certainly terrestrial interference, which is not the same as proven terrestrial. This is not conspiracy thinking, it is precision. The case for BLC1 being artificial interference from Earth is strong. The case is not absolute. The question at Proxima Centauri remains, as it has always been, stubbornly open. This is the destination. A tidally locked world, perpetually half-roasted and half-frozen, battered by flares from a dim red star, stripped perhaps of its atmosphere, harbouring perhaps some form of radiation-hardened life in its rocks or under its oceans, or somewhere we have not yet thought to look, or perhaps harbouring nothing at all but the quiet chemistry of a world that never quite made it past the threshold of biology. We do not know, and the not knowing is the most powerful argument for the going. The question is never quite whether humanity will go to Proxima Centauri. Given enough time, given sufficient development of civilization and technology, the physics does not forbid it. The question is always about sequence. What is the next step on the path? The one that follows from where we actually are right now. And the honest answer is that we are at the very beginning of the very first chapter of the Interstellar story. Not the middle, not the late second act. The first scene of the first chapter. The moment where the hero looks at the map for the first time and realises how far the journey is. Voyager 1, as we have noted, represents the current outer edge of human physical presence in space. A 722 kilogram spacecraft, launched by a Titan IIe Centaur rocket with a propellant-based propulsion system, currently moving at roughly 17 kilometers per second through the interstellar medium. It will never come close to Proxima Centauri, but it did something that we should not undervalue. It crossed the heliopause, the boundary at approximately 120 astronomical units where the Sun's influence ends and the true interstellar medium begins. It became the first human-made object in interstellar space, and the data it has returned about the density of the interstellar plasma, the structure of the magnetic field at the heliospheric boundary, the intensity of galactic cosmic rays beyond the solar wind's protective influence, is genuinely irreplaceable. It is the first direct measurement of the environment our spacecraft would need to traverse on any interstellar journey. The next step on the observational ladder is the proposed Interstellar Probe mission, a concept studied extensively for NASA and presented to the 2023 Planetary Science Decadal Survey. The Interstellar Probe would use a Jupiter gravity assist followed by a solar flyby, dipping within 10 solar radii of the Sun's surface, using the Sun's enormous gravity to gain velocity through the Oberth effect. to achieve a speed of approximately 15 to 20 astronomical units per year, roughly 5 times Voyager 1's current velocity. Over a 50-year mission, it would reach 400 to 1,000 astronomical units from the Sun, probing the structure of the outer heliosphere and the very local interstellar medium in unprecedented detail. It would not approach Proxima Centauri. It is not aimed there, and its velocity would still require tens of thousands of years to cover the distance. But it would characterize the road. It would take the first high-resolution measurements of the environment through which any future interstellar mission would have to travel. This is what the near term of interstellar exploration looks like. Characterization, reconnaissance, learning the terrain before committing to the crossing. The interstellar probe, if funded and built, would be followed by a generation of increasingly capable reconnaissance missions, each probing a little deeper into the interstellar medium, each refining our understanding of the dust density, the cosmic ray intensity, the magnetic field structure, the hydrogen number density, all the parameters that matter enormously for designing a faster, harder-hitting mission. Meanwhile, the propulsion technology landscape is evolving. The key developments to watch are 3: nuclear thermal propulsion, nuclear pulse propulsion, and directed energy propulsion. Nuclear thermal propulsion, heating a propellant by passing it through a nuclear reactor rather than burning it with chemical fuel, was demonstrated in ground tests in the United States in the 1960s and early 1970s under the Enerva program, which achieved specific impulses of roughly 825 seconds, more than twice the best chemical rockets. It was cancelled for political and budget reasons. Its successor technologies are currently under development at NASA and DARPA under the Draco program, aimed initially at cislunar and Mars missions, but with a technical foundation that could, in principle, be scaled and extended toward interstellar precursor missions, achieving velocities of 100 to 200 kilometers per second, still far below what is needed for Proxima, but vastly faster than anything currently available. Laser propulsion, the technology underlying breakthrough Starshot, has a more speculative but arguably more transformative potential trajectory. The laser array required for Starshot does not yet exist, and building it represents a technical and financial challenge that dwarfs any current space program. But the fundamental physics is sound. The material science of ultra-thin reflective sails is advancing, and the miniaturization of electronics continues to make the nanocraft concept more plausible with every generation of technology. The Breakthrough Initiatives program continues to fund research into both laser arrays and sail materials. An AI-designed light sail concept, developed in 2024, demonstrated that machine learning could optimize sail geometries in ways that human engineers had not anticipated, reducing thermal stress and improving reflectivity simultaneously. This is not a breakthrough in the sense of solving the problem, but it is a demonstration that the problem space is actively being explored by increasingly powerful tools. The deceleration problem, the inability of any current directed energy concept to also slow the craft at the destination, has generated a range of ingenious proposed solutions beyond the magnetic sail. One concept, proposed by physicist Renee Heller and colleagues, involves using the light from Proxima Centauri itself to decelerate the incoming sail. If the sail is designed to be reflective on both faces, the light pressure from Proxima, encountered at increasing intensity as the craft approaches, could act as a braking force. The mathematics are challenging. The deceleration from stellar light pressure at 0.2 c approach velocity is modest, and a spacecraft would need to spend a significant fraction of the star's habitable zone in a tightly controlled braking maneuver to slow to orbital velocity. But it is physically possible, requires no additional fuel or infrastructure at the destination, and has been subjected to detailed mathematical analysis that supports its feasibility in principle. There is also the question of what an arriving probe, even at the flyby velocities of a Starshot nanocraft, could actually tell us about Proxima b. The answer, at current technology levels applied to a gram-scale payload, is genuinely limited. 5 subgram cameras with 2 megapixel resolution, operating during a few hours of close approach at 0.2 C, would have exposure times so short and angular velocities so high that image quality would be severely compromised. Communication bandwidth from a transmitter the size of a postage stamp across 24 light-years of interstellar space would be severely limited. The first Starshot data, if the concept worked exactly as planned, might be a handful of blurry images and a few megabits of atmospheric spectral data, precious beyond measure compared to what we now have, but a long way from answering the central question of whether life exists there. The subsequent generation of missions, built on the success of the first, informed by its data, benefiting from a technology base that has advanced by another decade or two, could be more capable. Larger sails, higher laser power, better electronics, more capable deceleration mechanisms. The trajectory of the technology, if breakthrough Starshot or its successor programs are pursued seriously and funded adequately, points toward increasingly capable probes over the second half of this century. None of them, in the current scientific consensus, would be crude, but all of them could fundamentally change what we know about the nearest star system, about the atmosphere and surface of Proxima b, about whether life has taken hold in the closest solar neighbourhood. The crude mission, by contrast, lives on a timescale that we should be honest about. The fundamental propulsion problem, getting enough energy, efficiently enough, into a spacecraft that is large enough to support human life for years or decades, requires technologies that do not exist and whose development timescales are measured not in years but in generations. Fusion propulsion, the most promising of the physically plausible candidates, has been 20 years away from practical implementation for approximately 60 years. The ongoing progress in fusion research, including the 2022 National Ignition Facility, result achieving fusion ignition for the first time, and the subsequent 2023 and 2024 results achieving increasing energy gain, provides genuine grounds for measured optimism, but the path from ignition in a laboratory to a sustained shipborne propulsion system that can burn for years is not a short one. It is possible that a crewed mission to Proxima Centauri could be launched in the 22nd century. Given the pace of technological development, the depth of the scientific motivation, and the demonstrated capacity of human civilization to achieve things that seemed impossible when they were first proposed, the moon landing, the sequencing of the human genome, the construction of the Large Hadron Collider, I do not think it is reasonable to call a crewed Proxima mission a fantasy, but I also do not think it is reasonable to call it an engineering project. It is currently a vision, and the distance between vision and engineering project is exactly the distance that separates our current civilization from the one that could execute the mission. What changes the calculation is motivation, the detection of life, or even of compelling biosignatures that could not be explained by abiotic chemistry, in the Proxima system would transform the motivation for an interstellar mission from interesting science to the most urgent question in human history: the political will, the economic resources, and the public imagination that would be directed toward reaching Proxima b in the decades following such a detection would be unlike anything that has ever been directed toward a scientific goal. We do not know how quickly a sufficiently motivated, sufficiently resourced civilization could develop the required technology. We have never tried. The closest analogue is the Apollo program, which took the United States from no human spaceflight capability to landing on the moon in 8 years under conditions of extreme political motivation and effectively unlimited funding. The gap between Apollo and an interstellar crewed mission is vastly larger than the gap between no human spaceflight and the moon. But so is the gap between 1961 and wherever we will be 100 years from now. The Proxima system will wait for us. Red dwarfs age slowly, burn gently, and endure for hundreds of billions of years. Proxima Centauri has perhaps 95% of its main sequence lifetime remaining. Whatever is in that system, whatever chemistry, whatever geology, whatever biology, has been there for 4.85 billion years and will be there for a very long time after us. The urgency is not the destination's, the urgency is ours. The question of whether any intelligence has ever made this crossing, whether some other species, somewhere in the galaxy, has looked up at a dim red star and asked, "What is there?" and then actually gone, is one that the search for extraterrestrial intelligence has implicitly been probing for 7 decades without a definitive answer. The Fermi paradox, the observation that the universe appears old enough and large enough to have produced countless civilizations, yet we see no evidence of any of them, hangs over the entire conversation about interstellar travel like a question that nobody quite wants to ask too directly. If interstellar travel is possible, and if even a small fraction of civilizations eventually achieve it, then the galaxy should be colonized, or at least visited by now. The fact that it appears not to be carries an implication that is worth sitting with, even if we do not have the tools to resolve it. Perhaps the great filter lies somewhere in this journey, in the propulsion problem, the radiation problem, the biological problem, the psychological problem. Perhaps every civilization that develops the technology to look at the stars eventually discovers that the stars are too far away, the barriers too numerous, the cost in life and resource too high, and turns its attention inward instead. Perhaps the crossing is possible but so expensive that no civilization that has managed to reach a sustainable equilibrium would choose to make it. Perhaps the universe is full of civilizations that can see each other and cannot reach each other, and have found ways to be at peace with the gap. Or perhaps the crossing is possible and some have made it, and we simply have not been looking in the right way, at the right frequencies, with the right instruments, toward the right targets. Perhaps Proxima Centauri is not empty, perhaps the answer to BLC-1, not the mundane technical answer about terrestrial radio frequency interference, but the deeper question it was, however briefly, allowed to represent, is not yet in. Consider light. The light reaching your eyes from Proxima Centauri right now left that star 4.24 years ago. Not metaphorically, not approximately. The photons arriving at your retina at this moment were emitted from that dim red ember 4 years and 3 months in the past, before they began the long crossing of interstellar space to arrive here, to arrive at you. When you look at Proxima Centauri through a telescope on a clear southern hemisphere night, you are not seeing it as it is, you are seeing it as it was. You are always, when you look at the stars, looking into the past, and the further away the star, the deeper into the past you look. This is not a poetic conceit. It is the literal geometry of a universe in which light travels at a finite speed and information cannot exceed it. What it means, in a way that I find genuinely moving and that I want to spend a moment with, is that the act of looking at Proxima Centauri is itself an act of reaching through time. The astronomers who first measured its parallax in the late 19th century were receiving light that left the star before their grandparents were born. Guillaume Anglada Escudé and his team, during those months in 2016 when they were watching the star wobble, were receiving light that had been travelling through the void since 2012, since before the discovery was even begun. The Breakthrough Listen team, during the observations that would later reveal BLC-1, was receiving signals that originated, wherever they originated, in the spring of 2019, before the first reports of a novel coronavirus emerged from Wuhan, before the world changed in ways none of the astronomers monitoring Proxima that night could have anticipated. There is something in this that speaks to the human condition at a level deeper than science. We are always reaching towards something that is not quite here, not quite now. The star we see is not the star that is. The data we analyse reflects conditions that have already evolved. The questions we ask about Proxima Centauri b, does it have an atmosphere? Does it have water? Does it have life? May already have answers at the planet itself. Answers that exist in physical reality right now, 4 light-years away, while we sit here unable to know them. The universe is full of unanswered questions that are only unanswered from our perspective. The answers exist. We simply have not yet found a way to receive them. Every generation that has looked at the night sky has faced this gap between question and answer, between reach and grasp, between the world as we know it and the world as it is. The ancient Greeks who catalogued the stars did not know they were looking at fusion reactors. The astronomers who first resolved them into parallax measurements did not know they were charting the potential homes of other worlds. The Voyager engineers who aimed their probes outward into the solar system in 1977 could not have known that within a decade we would discover thousands of exoplanets, and that the nearest of them all would be sitting right next door to the destination they never quite reached. Each generation sees further than the last, and each generation's horizon becomes the next generation's starting line. We are, right now, at the moment in the story where the destination has come into focus. Proxima Centauri b is not a theoretical possibility. It is a real object, with a real orbit, at a real distance, potentially with real water and real chemistry, and, perhaps, a real answer to the question we have been carrying since we first looked up. We can see the shore, we cannot yet swim the ocean. The gap between those two statements is the entire project of the next several generations of human civilization. The development of propulsion, the protection of biology, the sustaining of psychology, the engineering of structures that can survive decades in a particle sea, the building of a civilizational commitment robust enough to outlast any individual life, any presidency, any economic cycle, any catastrophe short of extinction. And yet, here is the thing that, more than any other, makes me believe the journey will eventually be made. The human species has a demonstrated, repeated, extraordinary habit of doing things that could not be done until they were. The pattern is always the same. Someone looks at the gap between where we are and where we need to be, and says that is too far, that is impossible. No reasonable analysis of current capability suggests that it is achievable, and then eventually it is achieved. Not easily, not quickly, not without sacrifice, without failure, without the loss of people who gave everything to the attempt. But achieved: the moon, the genome, the direct imaging of a black hole, the detection of gravitational waves from colliding neutron stars a billion light-years away. These were not reasonable expectations at the time they were proposed. They were visions. And visions, when they are backed by the genuine conviction that the answer matters, that the question is worth the cost, have a strange and persistent tendency to become engineering programs. I do not know who will first cross the gap to Proxima Centauri. I do not know what century they will live in, what technology they will use, what they will find when they arrive. I do not know whether they will be recognizably human in the biological sense, or whether centuries of space travel and perhaps deliberate biological modification will have made them something different, something more suited to the void, more tolerant of radiation, more patient with the long dark. I do not know whether the planet they find will greet them with a surface of iron-dark vegetation drinking up a red star's meagre light, or with a barren rock scoured clean by 10,000 years of superflares, or with the particular silence of chemistry that has never been stirred into life. But I find it genuinely extraordinary, in the most literal sense of that word, not the exhausted colloquial one, that we are the generation that asked. We are the ones who pointed the spectrograph at the nearest star and said, "Wobble for me." And it wobbled. We are the ones who measured the wobble and calculated the planet and called it by a name, Proxima Centauri b. We are the ones who began designing the spacecraft, writing the physics, building the lasers, arguing about the biology, losing sleep over the radiation environment of a world we have never seen directly and may not see in our lifetimes. We are the generation of the question. Someone else will be the generation of the answer, and between the question and the answer, there is 40.14 trillion kilometers of physics to cross, of dust and cosmic rays and time dilation, and the particular loneliness of the long dark between the stars. The light that left Proxima Centauri 4 years ago is arriving right now. What it is carrying we cannot yet say, but we are learning to listen.